Hi. In the first lesson, we learned about functions, a pre-calculus idea that I told you would be used in every day that we're talking about calculus. Functions are very useful, but it's something you already know how to do, so we're not going to spend much time doing that. You have a function like f of x equals 5x. You put 4 into that function, and you get 5 times 4, or 20. And sometimes that number is very valuable. Well, what we're going to talk about today is the second thing we're going to do with functions, and that's to take a limit of a function. Now, limits themselves are not all that important, but they are fundamental in the development of the third and fourth thing that we're going to do with calculus. I'm not going to tell you even their names yet. It's so exciting to wait for that. So right now, we're just going to learn about what a limit is, so we can learn about these other really important things we're going to do to functions. So, first of all, here's the definition of a limit. Limits are values that the function, and this is important, seems to be approaching as the independent variable, which yesterday we said oftentimes the independent variable is x, approaches a value from both sides. So all that's really saying is if you've got a function y equals f of x, where x is the independent variable and y is the dependent variable, what we're trying to do is saying as x gets really close to this value a, which might be 1 or 2 or 3, who knows, from both directions, as you start to get closer and closer, what does the function value, what does the y value seem to be approaching? So, let's see if you can do a problem without me even showing you anything more. Well, this is how you say in mathematical symbols what I'm saying up here. You're saying the limit as x approaches a of f of x, and the answer is the limit, or L. So, if in place of f of x we put the function x squared, and in place of a we say the number 3, what is the limit as x approaches 3 of the function x squared? What does x squared seem to be approaching as x gets close to 3 from both directions? So if you took 2.9999 and squared it, or 3.0001 and squared it, what are we going to be getting close to? I bet a lot of you are saying 3 times 3 is 9. And that's exactly right. So, not all limits are going to be that easy, but the idea is very much the same. Now, because I'm saying from both sides, besides this terminology right here, we have two very similar terminologies. The limit as x approaches a from the right of the function f of x, and the limit as x approaches a from the left of f of x. Then we're trying to see, this is what we call a right-hand limit, which is trying to find out when you're only approaching a from values bigger than a, from the right-hand side of a, and this is from the left-hand side of a. Now, as it turns out in this problem, what's to the right of 3? 3.0001. As you approach it from the right, you're getting close to 9. So if this were, instead of f of x, if this were x squared, the answer would be 9. The limit as x approaches 3 from the left, if that was x squared, would also be 9. So sometimes the limit from the left equals the limit from the right. In fact, if you look at the definition, if the limit really does exist, then the limit from the left has to equal to the limit from the right. That's a theorem. But that theorem really doesn't have to be proved because it comes directly from the definition of what a limit is. So, this is what we're going to try to do when we're finding limits. It doesn't even look like a very mathematical definition, but it's very useful, and it's, I think, the easiest way usually to solve one. Now, there is a more mathematical definition. You could say the limit as x approaches a of f of x equals L if and only if for every value of epsilon greater than 0, there exists a delta greater than 0 such that the magnitude of the distance from f of x to L is less than epsilon whenever the magnitude of the distance from x to a is less than delta. Now, that's a very eloquent definition of what a limit is, and it's very much more mathematical, but it's also a bit confusing. I'm not going to, it's something that you're probably, unless you go into math at a much higher level, you're probably not going to have to use this definition. But I want to just quickly show you what it means. That means if you pick any small number epsilon, no matter how small, that we can get close enough to, we can get our function f of x close enough to L within some distance epsilon, as long as we get close enough with our x value to a. So it's basically saying the same thing, but in much more mathematical terms. Now, if you seem a little bit confused about this, it would take a little bit more thinking about it in order to be able to really understand that deeply. But I did want you to get to know this. We're not going to use it when we actually go to take limits. But I want you to understand that this theorem that we're going to do next, which is a very valuable theorem, has to be proved using this definition because it's so mathematical. Now, the theorem says this: if you have two functions, f of x and g of x, and you're approaching a with both on both functions, so if the limit as x approaches a of the function f of x is some limit L1, and the limit as x approaches a of another function g of x is L2, like this might be 7 and this might be 3, then the limit of the function that you get by adding f of x to g of x as x approaches a turns out to be L1 plus L2. So if the limit of the first one was 3 and the limit of the second one was 7, the limit of the function f of x plus g of x would be 3 plus 7, or 10. Kind of the way we would hope that it would turn out. And the same thing happens with subtraction. And guess what? If you had a function that just had a constant out front of it, then you can just take the limit as x approaches a of f of x, and then when you get done, multiply it by that constant. Again, this is pretty much how we would hope that things would work out. And guess what? It even works with multiplication. So the limit of f of x times g of x would be L1 times L2, and it even works with division. So this would be L1 divided by L2. With one caveat, L2 cannot be 0. If for some reason the limit of this function happens to be 0, we still can't divide by 0. Now, this is kind of my own thing, but to me, this looks so complicated, this theorem, and it's so helpful. There's an easier way you can remember this than to try to remember all these symbols. And I just say, limits are our friends. And if you remember that, we know that when we're taking a limit, that they act just the way we would hope they would be. So just keep that in mind in the future. Okay, so that pretty much covers what a limit is. So let's just look at a couple of examples. Some ones that are a little bit more difficult than that first one. Well, here's one right here. The function is more complicated looking. And it's not quite as easy as this one because we can't just plug in 2 because we cannot divide by 0. So what do we have to do? Well, this is where algebra comes into play. I think we can simplify this. When we plug 2 into the numerator, you also get 0. So from the fundamental theorem of algebra, we know that that numerator can be factored, and one of the factors has to be x minus 2, and with a little bit of thinking, you can get the other factor to be 2x plus 1. And then what happens? This factor cancels with this factor, and you find out that that really complicated looking function is really a much simpler function. It's really just a straight line, with the one exception. This straight line has no holes in it. You can put any value of x into it, where we know this function you can't. So really, this complicated function is just like the function y equals 2x plus 1, except that x equals 2, there's a little hole there. We don't really have a function value at that point. But given that, what does the function seem to be approaching as x approaches 2? Well, from the left and to the right, as x gets close to 2, this gets close to 5. It's now just as easy as this problem was. If we just cover that up, what's the limit as x approaches 2? It's just 4 plus 1, or 5. And that is the answer to that limit. Okay, let's try another one with an absolute value in it. Well, again, we can't just plug it in because we can't divide by 0. But think about it. We can go back to this theorem right here. Can we see what happens as x approaches 0 from the left? What's the limit as x approaches 0 from the left? Well, from the left, the absolute value of x over x, what do those values look like? Like, take the number -2. What's the absolute value of -2 divided by -2? It's just -1. So, and it doesn't matter what negative value you put in there, you're going to get -1. So from the left, you get -1. Now, how about as you're approaching it from the right? Well, when you're looking at to the right of x equals 0, those are all positive values. So if you take the absolute value of any number divided by that number, if it's a positive number, you're going to get 1. So really, this just becomes 1. So the limit from the right side is 1. Since the limit from the left doesn't equal the limit from the right, we know from this theorem that this limit does not exist. And if you were to graph it, this is what it would look like. The function would look like 1 when you're to the right, and it would look like -1 to the left, and there would not be a value at 0. And you can see the limit from the left doesn't equal the limit from the right, so the limit doesn't exist. Whereas this one, the limit from the left does equal the limit from the right. Okay, so let's try another one. Again, when you go to plug 0 in, you're dividing by 0. But this time it's not 0 over 0 like these two were. This is a number divided by 0. So let's see. What's the limit as x approaches 0 from the, let's do from the right first. Think about what happens if you took a number like to the right of 0, like 0.001, and squared it. You're going to get a really, really small number. And if you take 1 and divide it by that really small number, you're going to get something really big. So this is going to actually approach a huge number. It's going to approach infinity. Now, if you approached it from the left, now, to the left of 0, the numbers are like -0.0001. But in this case, we're squaring it, so you're still going to get the same thing you had in the first. So we get infinity. So at this point, you could say the limit equals infinity. Now, sometimes, since we're talking about limits being real numbers, and infinity is a concept, not a real number, you're also allowed to write does not exist, because there really isn't a number. What's happening on this function, 1 over x squared, it's going to infinity from this direction, and it's going from infinity to that direction. So in both cases, it's approaching infinity. But since infinity isn't a number, you would be allowed to say does not exist. Now, what if you don't even have a function, you just have a graph of the function? Then you don't, if you follow this definition, all we have to do is see where the function seems to be going. So, say we have this function y equals h of x. What's the limit as x approaches 1 of h of x? Well, to do this, here's x equals 1 right here. You can kind of see there's not even a function value there. But that, remember, it doesn't matter if there's a function value there for limits. So all we have to do is see where it seems to be approaching. But before we can do that, before we can even answer this question, we really have to answer what's it approaching from the left and what's it approaching from the right. So from the left, what does the function value seem to be approaching? It seems to be getting close to 2. From the right, it also seems to be getting close to 2, the function value. So we just say 2. We can just follow with our fingers to see what it seems to be approaching from the left and from the right. Now, -1 is slightly different. Here's x equals -1 over here. Well, let's try the same thing. What's the limit as x approaches -1 from the left-hand side? The function seems to be getting close to -2. Okay, that could actually be a problem you get on a test. You just say -2. What's the limit as you're approaching from the right? Well, just follow with your fingers. What does the function seem to be approaching? The function value seems to be approaching 0. That also could be a problem on a test. And in order to answer, well, I'm sorry, I had meant this one to be from the left. My mistake. Okay, so We found out from the left the answer is -2. From the right, it's 0. Now we could answer the question, what's the limit as x approaches -1 without a from the left to right, just a regular limit. Since the limit from the left doesn't equal the limit from the right, we would say does not exist. So, sorry if I confused you there. I was thinking I was going from the left. This is the limit from the left. This is the limit from the right. If you really want to know the limit of the function as x approaches -1, you have to first get these two answers. And when you see that they're not the same, then we would say it does not exist. If they did turn out to be the same, then that would be the answer for that one. Okay, I'm going to end this with just one more, what we call a piecewise function, where the function is x plus 2 when x is less than 1, and 4 minus x squared when x is greater than or equal to 1. We could actually graph this out and do the same way we did this way, but that's quite a bit of work. So let's just think about it. What's the limit as x approaches 3 of the function g of x? Well, we have to see, which function are we using at x equals 3? Well, 3 is greater than or equal to 1. So we're only really in this bottom function. So we can say, what's the limit as x approaches 3 of this function? It's 4 minus 3 squared, or -5. That was easy. We only had to look at one of the functions. Now, the only number that it's going to be more difficult is at x equals 1, because 1 is on the borderline of these two functions. So again, we're going to have to look from both the left and the right. So, what's the limit as x approaches 1 from the right? Well, from the right, bigger numbers than 1, we're going to be into this function, x greater than or equal to 1. So what's the limit as x approaches 1? 4 minus 1 is 3. What's the limit as x approaches 1 from the left? From the left, we have to use this function, because to the left would be less than 1. So what do you get when you plug in 1? 1 plus 2 is 3. Those two functions, this parabola and this straight line, must come together at that point. So we could say, since the limit from the left equals the limit from the right, the total limit equals 3. So there's 5 examples that give a lot of different ways that you could be asked limits, and they really don't get too much more difficult than that. So I'm hoping that gives you a pretty good idea of limits. There's still a few more things we have to learn about them, but they will come in the next videos that we do. So thank you very much, and hope you enjoyed this. Have a good rest of your day.